Welcome to the office. We want to take a look at an example that deals with conjugacy. Let's remind ourselves first of what it means for two subgroups to be conjugate of one another. So a subgroup H is conjugate to a subgroup K of a group G, right? So two subgroups H and K in the group G are conjugate to one another if there exists an automorphism such that the image of H is K. So what is an inner automorphism? Well, if we refer back here a moment, an inner automorphism is the mapping I sub G from G to G, where it's defined as IG of X is GX inverse. Wonderful. So a subgroup is conjugate. Yep, there we go. Okay, so we want to show that conjugacy is an equivalence relation on the collection of subgroups of G. So we're not necessarily talking about one specific G, but rather we're talking about any pair of subgroups are conjugate to one another if there exists this relationship between them. And we want to show that this is an equivalence relation. So let's see if we can work through this. Now, if we want an equivalence relation, we want to show that this thing is reflexive. So let's let H be a subgroup of G. So that is less than or equal to, not subset containment there, right? That the sharp pointed. There we are. So that is our subgroup notation. Then for some element or for the element E in G, the identity, what we can do is we can observe that I sub E of the subset H is exactly the group H. Okay. So the image of the group H is H itself, right? Because this is just giving us exactly the input back, right? Our EXE is just X. So we have an inner automorphism from H to H. Thus, H is related to H. And R, that is the idea of conjugacy, is reflexive. So the conjugacy equivalence relation I am denoting by R in this case. All right. Let's talk about symmetric here. So I want to let H and K be subgroups of the group G such that H is related to K. Then there exists a G in G such that I sub G of H is equal to K. That's what it means for two subgroups to be conjugate of one another, right? H is conjugate to subgroup K if there exists G such that this. Fantastic. So H is related to K. Now I want to show that K is related to H, right? That's what symmetry is. I can write it in either order. So how can I do that? Well, let's see here. I want to consider, let's see here. Make sure I get this right. Yes, okay. So the image of H is this, and that tells us that G inverse is K. Now we essentially have this really nice ability to multiply, right? Because we're talking about cosets, I can perform some manipulations, and I can say that I can multiply on the left by G inverse. I'm not going to go through all of the algebraic manipulations here, but this is going to give us that H is equal to G inverse KG. Multiply on the left by G inverse, multiply on the right by G, and that gets me this. Then for G inverse, which is an element of G, of course, the image of, the inner automorphism using G inverse of K is equal to H. That's what this says right here. Thus, H is related to K, and R is symmetric. Excellent. So I've identified an inner automorphism that shows that K is conjugate to subgroup H. I've changed the order there. Now I want to observe transitivity. So transitive, I want to let H1, H2, and H3 be subgroups of the group G such that H1 is related to H2, and H2 is related to H3. So I've got three subgroups. H1 is related to H2, and H2 is related to H3. This is going to give us, then there exists G1, G2 elements of G such that the inner automorphism using G1 of H1 is equal to H2. That's H1 is related to H2. And the inner automorphism using G2 of H2 is equal to H3. Now this sounds good, fine, and wonderful. And really all that I want to do here is recognize that I have functions, domain, range, right? That's essentially the idea, and then domain and range. Well, the range of this function is the domain of this function. The outputs of this function are the inputs to that one. That's what I'm looking for there. No, really, these are taking all of G, and the output is all of G, but I'm interested in specifically, this one has an input of H1, this one has an output of H2. So if I compose these functions, I can observe that the composition I sub G1, and actually I want I sub G2 composed with that of H1 is equal to IG2 of IG1 of H1, which is equal to H2, not H2 overall, but IG2 of H2, which is or H3. There we go. So I end up with this, but I also can observe that I sub G2 composed with I sub G1 of H1 is IG2 of G1 H G1 inverse, which is G2 G1 H G1 inverse G2 inverse, which is G2 G1 H G1 inverse G2 inverse, which is, of course, G2 inverse, G2 G1 H G2 G1 inverse. There we go. That is for G1, G2, an element of G, we have that I sub G1, G2, G2, G1, actually. The order is incorrect there. G2, G1. I sub G2, G1 of H1 is equal to H3. And H1 is related to H3. So here I pretty much had it. I observed that the composition gave me H3. That was very nice, but I needed to recognize that that composition could be expressed very explicitly as one inner automorphism. And that's what this work here allowed me to observe. So look, this is an inner automorphism that gives that takes H1 and gives me back H3. So that way I know that they are related through this conjugacy. So are is transitive, which allows us to conclude, therefore, the conjugacy that we're interested in, let's see here, conjugacy, therefore conjugacy is an equivalence relation. So we find the discussion of equivalence relations to continue through to the end of the semester, right? That's something that came from early on in this course. This problem also asked us to characterize the normal subgroups, but in reality, that was already done for us back here in our previous video, right? We said with this idea of conjugacy, GH is equal to HG if and only if IG of H is H. So in terms of the conjugacy, this equivalence relation and the equivalence classes, right? The cells where they appear in the partition, right? That's a different way of saying equivalence classes. The equivalence classes, the equivalence class for H, a normal subgroup, is just H. Okay. So an equivalence class is a set of things, and this set of things is the set of subgroups that are conjugate to one another. Well, according to the previous definition, we observed that for a normal subgroup, that is left and right cosets are the same, we would have to have that the only conjugate to a normal subgroup is itself. So when we go to look for when we go to look for a normal subgroup, if we were to consider this idea of conjugacy, we're just looking for those groups that are only related to themselves under this equivalence relation. Excellent. That's all I wanted to share for now. So join me back in the office for another example.